This question asks for the electric field at point P, which is 5 centimeters above, that distance is 5 centimeters, above a charged rod. The charge is minus 10 microcoulombs and the length of the rod is 30 centimeters. So we'll begin this the usual way. You pick a little element of charge, dq, that's right here, dq. You draw the element of electric field, which points straight down because the charge is negative, so it points into a negative. So here's our element of electric field, dE. We write that our dq is the charge density times the length, so lambda, which is going to be q over L. The length is a little bit in the y direction, dy, so dq equals lambda times dy. Our x component of electric field will of course be 0 because there are no x or y components. Our y component of the element of electric field is k times dq over r squared. Let's be careful about r. R is your distance from your point to your charge dq. So r is from here to here. So this is our r value. So let's fill in our lambda, or our dq. So k times lambda times dy over r squared. Doing our integral, we've got to be careful. This is r here, this is a variable. This is our dy here, so y is a variable. We either need to write dy in terms of dr, or we have to write r in terms of y. I'm going to choose to write dy instead of in terms of dr. So r is up and down, y is up and down, so a little bit of length with regards to r would be the same as a little bit of length with regards to y. So we have k times lambda times dr over r squared. There's our y component of the element of the electric field. Our total electric field Ey will be the integral of this. So Ey is the integral of dEy. So it's the integral of k times lambda times dr over r squared. Take the k and the lambda out front. To think about our limits of r, so r varies from the top of the rod to the bottom of the rod, or from the bottom of the rod to the top of the rod, doesn't matter which way. Let's take from the bottom to the top. So at the bottom of the rod, r is 35 centimeters, because this is the origin, this is 35 centimeters. So at the bottom, at our beginning value of r, it is 0.35 meters. At our top, we're at the top of the rod, that's 5 centimeters away. So now we're ready to keep going with our integral. We've got k times lambda. The integral of 1 over r squared is minus 1 over r. That's just your power rule. That's going to be evaluated at 0.05 meters, 0.35 meters. So we'll fill in our values. K times lambda minus 1 over 0.05 minus 1 over 0.35. And now we can put in our numbers. K is 8.99 times 10 to the 9 newtons per coulomb. Newtons times meters squared over coulombs squared, sorry. Lambda is our charge density. We can use the magnitude if we want, or we could put in the value, which would be negative. Let's just put in the magnitude. Let's put in the q over the L. So the q is minus 10 times 10 to the minus 6 coulombs, divided by the length of the rod, which is 30 centimeters. And then minus 1 over 0.05. Minus times minus gives us a plus. And we'll work that out in our calculator. This will turn out to give us a positive number, 5.14 times 10 to the 6 newtons per coulomb. Now, if we look at our electric field vector, we see that it points down. We know that it has to be negative. So we know that our Ey has to have a negative value. And then our net electric field only has the y component because the x component equals 0 because it doesn't point left or right at all. So our total electric field is minus 5.14 times 10 to the 6 newtons per coulomb in the y direction, J.